Euclid Maths presents.
Hi everyone, I am Dr. VSK. Welcome to my series of lectures on topology. In this present lecture, let us see what are open sets and closed sets in a topological space. To define an open set in a topological space, consider a non-empty set X together with a topology T. In this topological space X, T, a subset G of X is said to be an open subset of X if G is a member of T. A subset F of a topological space X is said to be closed in X if its complement F complement equals X minus F is open in X. Observe that in a topological space, complements of open sets are closed and complements of closed sets are open. Consider a collection set of G alpha such that alpha belongs to delta of all open sets in a topological space X, T. In this collection, each G alpha is an open subset of X. Since each G alpha is open in X, G alpha is a member of T for each alpha belongs to delta. Since T is a topology on X, it contains open sets. So each G alpha is a member of T. Then union of all these G alphas is also a member of T. Hence, union G alpha where alpha belongs to delta is an open set in X. Thus, arbitrary union of open sets is open in X. If G1, G2, so on, G suffix n is any finite collection of open sets in a topological space X, T, then they are all members of T. That is, each G suffix I is a member of T for I is equal to 1, 2, so on n. Since T is closed under finite intersections, the intersection G1 intersection G2 intersection so on intersection Gn is a member of T. So G1 intersection G2 intersection so on intersection Gn is an open set in the given topological space X, T. Thus, intersection of any finite collection of open sets in a topological space is always open. Observe that finite intersection of open sets is open. Consider an arbitrary collection set of F suffix alpha such that alpha belongs to delta of all closed sets in a topological space X, T. Since each F suffix alpha is a closed set in X, its complement F alpha complement equals X minus F alpha is open and it is a member of T. Because T contains all open subsets of X. Since each F alpha complement is a member of T, their union F alpha complement where alpha belongs to delta is also a member of T. That is, union F alpha complement where alpha belongs to delta is open in X. We can write union F alpha complement where alpha belongs to delta equals intersection F alpha where alpha belongs to delta whole complement. So, intersection F alpha where alpha belongs to delta whole complement is open in X. Since the complements of open sets are closed, intersection F alpha where alpha belongs to delta is closed in X. That means the intersection of any collection of closed sets is closed in X. In other words, arbitrary intersection of closed sets is closed. If F1, F2, so on Fn is any finite collection of closed sets, then their complements are all open sets. That is, F1 complement, F2 complement, so on Fn complement are open sets. Then their intersection, F1 complement intersection, F2 complement intersection, so on intersection, Fn complement is open because finite intersection of open sets is open. We can write F1 complement intersection, F2 complement intersection, so on intersection, Fn complement equals F1 union, F2 union, so on union Fn whole complement. Hence, F1 union, F2 union, so on union Fn whole complement is open. Since complement of an open set is closed, F1 union, F2 union, so on union Fn is closed. Hence, finite union of closed sets is closed. Observe that the union of any finite collection of closed sets is closed. Consider a 3-point set X equals set of A, B, C. Let T equals the empty set phi X singleton A, singleton B and set of A, B. In this topological space, let us find out what are open sets and closed sets. In this topological space, the open sets are the members of T. They are the empty set phi X, singleton A, singleton B and set of A, B. These are the open subsets of X. The complements of these sets are closed subsets of X. They are phi complement, X complement, singleton A complement, singleton B complement and a set of A, B complement that are X, the empty set of phi, set of B, C, set of A, C and a singleton C. So, in this topological space, the open sets are empty set phi, X, singleton A, singleton B and set of A, B. The closed sets are the empty set X, set of B, C, set of A, C and a singleton C. Observe that the empty set phi and X are both open and closed. Singleton C is closed but not open in this topological space. Set of A, B is open but not closed in this topological space. Set of B, C is closed but not open in this topological space. Similarly, singleton A is open but not closed in this space. In this example of a topological space, we have listed out all open sets and closed sets. Let's take another example. In this example also, let us consider x equals set of a, b, c. Take t equals set of phi, x. This topology T is the indiscrete topology on X, and this topological space x, t forms an indiscrete topological space. In this topological space, the empty set of phi and x are the only open sets and closed sets. The given set X has 8 subsets, but in this topological space, phi and x are both open and closed. The other subsets of x are neither open nor closed in this space. Observe that if we consider any topological space with indiscrete topology, then phi and x are the only open and closed subsets of x. Other subsets are neither open nor closed. Observe the following. Number 1. In any topological space X, the empty set phi and the full space X are both open and closed. Number 2. The union of any collection of open sets in a topological space is again open. Number 3. The intersection of any finite collection of open sets in a topological space is open. That is, finite intersection of open sets is open. Number 4. The intersection of any collection of closed sets in a topological space is again closed. That is, arbitrary intersection of closed sets is closed. Number 5. The union of any finite collection of closed sets is closed. That is, finite union of closed sets is closed. Consider any non-empty set X together with the discrete topology T. Then x, t forms the discrete space. In a discrete space, T contains all subsets of X. Since T contains all subsets of X, every subset of X is both open and closed. So, in a discrete space, every subset of X is both open and closed. In this present lecture, we have seen what are open sets and closed sets. Thank you all.